Hi everybody, this is Mrs. T from Mrs. T's Chem Talk AP Chem. I'm going to do another video here for more Ksp Practice. Those of you who don't know me, I'm Mrs. Tominello. I teach chemistry in Merrick, New York. So the last video that I put up, we were just introducing Ksp a little bit, and so this video is going to have a couple of practice problems and some of the things you might have to do for Ksp. Remember, talking about Ksp, we're talking about things that are very slightly soluble, that they really only dissolve to a very small degree. Some of the things you might have to do, you might have to find a formula, you might have to write the dissociation equation, find the Ksp expression, and using the Ksp, find what's called the molar solubility. So I'm just going to get this one started here. So the first thing they're saying here is that we're talking about aluminum hydroxide. So before we can really do anything, we have to find the formula for aluminum hydroxide. Knowing your polyatomics and knowing your charges is going to be really important here. Remember that polyatomics, when we crisscross and drop the signs, if a subscript comes down, it has to come down outside the parentheses. And so our formula winds up being AlOH parentheses 3. And we're going to be starting in our reaction with that as a solid. As that dissolves, it's going to dissociate into a small amount of aluminum plus 3 ions that are aqueous and hydroxide ions that are also aqueous. And because this was an understood 1 and this was a 3, the coefficients here are a 1 and a 3. We will then write our Ksp expression. And at the end of the last video, we discussed that these exponents here come from the subscripts because the subscripts give us the coefficients. So it's going to be Al plus 3. You could write a 1 or not write a 1 for the first power, and then OH minus to the third power. And again, remember that if we look and we highlight, we have a 3 here that came from a 3 here. This 1 gave us this 1, and then they match the exponents in the Ksp expression as well. Now, we have our Ksp, which is what this is all equal to. So this is equal to 4.6 times 10 to the minus 33 equals the Ksp, which equals aluminum concentration to the first power times hydroxide concentration to the third power. When we write our, either whether you want to call it a Rice chart or an ice chart for Ksp expression, because these are solids, we don't really include them at all because there is no such thing. We can't change the concentration of a pure solid or a pure liquid, so they don't come into our equilibrium calculations at all. Before the dissolving happens, these ion concentrations are 0, which means that before the dissolving, Q is 0, so that products will increase as we reach equilibrium. Plus coefficient X, this coefficient, plus coefficient X, again, this coefficient, and then we read down 0 plus 1x is x, 0 plus 3x is 3x. And I want to point out again that these coefficients match the subscripts, which match these coefficients, which match the superscripts. So now my Ksp of 4.6 times 10 to the negative 33 is equal to the equilibrium concentration of aluminum, which is 1x to the first, times the equilibrium concentration of hydroxide, which is 3x to the third, again noting coefficient, exponent, coefficient, exponent. They all came from the same place over here. And this is not supposed to be an 11, that's a 1. They all came from the same place. They came from the subscripts in the formula. And now we're going to see what X comes out to. Because when we find X, that is my molar solubility. Molar solubility is when we solve for X in the Ksp expression. So we want to be really careful with simplifying this, and this is going to be x times 27x cubed when we combine it. So this is going to be 27x to the fourth equals my Ksp. Remember, at any time you can always pause to get out your own calculator and do these calculations, but we're going to divide both sides out by 27, and then you can do 4 math 5 second answer to get the fourth root of that, and we're going to find our x. And the x for this one comes out to 3.6 times 10 to the minus 9. That is the maximum molarity of aluminum hydroxide that we can get to dissolve at whatever temperature this Ksp works for. So 3.6 times 10 to the minus 9 moles of aluminum hydroxide will be able to dissolve in a 1 liter total solution. So again, the Ksp is equal to the equilibrium concentrations of aluminum and hydroxide raised to these powers multiplied by each other. And when we solve out for x in a solution that has met the Ksp, that is the molar solubility. So this, oops, I didn't mean to do that. This 3.6 times 10 to the minus 9 molar is the maximum concentration of aluminum hydroxide we can get to dissolve at this temperature. If we want to calculate for silver acetate, and now instead they give us the molar solubility instead of giving us the Ksp, we're still first going to have to find the formula. So again, you're going to need to know your polyatomic ions and your charges on your metal and common metal and nonmetal ions. So Ag has a +1, acetate has a -1, which means that my formula is Ag C2H3O2. Again, we're talking about it dissolving to some extent, and since it's dissolving to some extent, we're going to make aqueous ions, 1 Ag plus for every unit, and 1 acetate for every 1 unit, which means that my Ksp is just simply going to be Ag plus C2H3O2 minus, because since these are each subscripts of 1, these are each coefficients of 1, these are each exponents of 1. And I am going to continue in this particular video to keep drawing and writing the ice charts or Rice charts, but we will not need to keep doing this once you notice that the subscripts match the coefficients and then match the exponents and the coefficients for the x's. So before the dissolving, each of these ions is at a concentration of 0. That makes Q 0, which means we have to shift towards the products in order to reach equilibrium, which means that each of these will go up by coefficient x, which means as we read to the equilibrium, it's going to be 0 plus x, 0 plus x, and at equilibrium, each of these concentrations will equal x. Now, we said that the molar solubility equals x. So in order to find the Ksp for this particular substance at this particular temperature, all we have to do is plug these two x's in. Now we know that each x equals 4.47 times 10 to the minus 2. If we square that number for this particular Ksp expression, this x goes in for Ag plus, this x goes in for acetate. Each of them is equal to 4.47 times 10 to the minus 2. When we plug that into the Ksp expression and calculate it out, we get our Ksp for silver acetate, 2.0 times 10 to the minus 3. And just for one more example, if we want to find or write the dissociation equation, the Ksp expression, and the Ksp for silver chromate, given that the molar solubility is 6.5 times 10 to the minus 5. Oops. And remember that 6.5 times 10 to the minus 5 is going to be my x in my equilibrium expression. Again, we have to know how to find the formula. Silver has a +1. Chromate, which is CrO4, has a -2. And when we crisscross and drop the signs, we get Ag2, CrO4. I can go directly from this expression and then say that that's going to be Ag plus squared CrO4 minus 2 to the first because of this subscript and because of the fact that that's an understood subscript of 1. I can further go in and say that that's going to be 2x squared, and that's going to be x, because remember, the subscript becomes the coefficient on the product side, which then also is the exponent in the Ksp expression, which is also the coefficient in the law of mass action as we're showing the going up by x. So I'm going to leave that there. I'm still going to go through the Rice chart to make sure that everybody sees where that came from, but those subscripts can directly go in as the coefficients for the x and can also directly go in as the exponents in the Ksp expression. So we have Ag2 CrO4 solid dissolving to 2 Ag plus aqueous, CrO4 2 minus aqueous. These coefficients become the exponents in the Ksp expression. Solid, initial, change is plus coefficient x, read down, and I wind up plugging in my 2x into the square and my x into the first, because these are my equilibrium concentrations. Equilibrium concentrations are the ones that are equal to the K. My x is equal to my molar solubility, so I can either combine this and then plug it in, or I can do 2 times, or I can do my 4x squared times x and just plug in the x in these two places, or I can combine it to 4x cubed and then plug in my x here. But either way, just be very careful with your plugging in on the calculator. Remember your order of operations, that we have to cube the x before we multiply by the 4, otherwise it's not going to come out right. So it's 4 times 6.5 times 10 to the minus 5 cubed. So cube this, then multiply by 4, and you're going to come out with your Ksp. And your Ksp comes out to 1.1 times 10 to the minus 12. So just to recap a little bit, we always need to find our formula first. Subscripts become coefficients in the dissociation equation. Coefficients become the exponents in the Ksp, because remember it's aqueous gas-only products over reactants to the power of the coefficients. And then because of the law of mass action, those coefficients also wind up being the coefficients for the x when we plug in. Molar solubility is the maximum concentration of something that can dissolve at a particular temperature that the Ksp is defined at. So the maximum concentration of silver chromate in water is 6.5 times 10 to the minus 5 molar. We can plug that in as the x when we get the Ksp expression, and that gives us 1.1 times 10 to the minus 12 for this particular Ksp. Hopefully that was another helpful practice for Ksp. If you have any other questions, certainly let me know.